So that's why at 150 Celsius, this is going to act more ideal than at 20 degrees Celsius. Again, like David said, gases behave more ideally when they are at a higher temperature and there's a lower pressure. So why is lower pressure important for being ideal? Think about what's happening on the molecular level for there to be lower pressure. Anyone have any ideas? Good guess. It's a good guess. Anyone? Why? David said earlier that this is true. Gases behave more ideally at higher temperatures and lower pressures. Higher temperatures make sense because the faster the gas molecules are moving, that means the less time they have to interact with each other. So that's one of those postulates that the ideal about gases is that they do not exert any forces on each other, right? So that's one of the postulates. So the faster a gas moves, less time it has to interact with one another. You can kind of think of it if you're running down a hallway and your friend's running the opposite way down the hallway and you're trying to high five each other, the interval at which you have to interact with each other is much smaller, so it's going to be very difficult to get that perfect high five, right? Whereas if you were walking, it would be a lot easier. So that explains the temperature aspect, but why pressure? Why is pressure? Yeah, exactly. So if there's less collisions between gas molecules, that means they're interacting less, which is one of the big things about being an ideal gas, right? So exactly. All right, 33, you can leave it. I'm gonna leave that one to y'all. Y'all don't have to solve that one. I don't think a single student has gotten that one right in the 5 semesters that I've done this. So we're gonna skip it just because I think I'm yet to see a question like 33 on the exam, so. But I mean, you can try it yourself.
Yeah.
I have yet to see a student get it right and yet to see a question like that on the exam.
Oh.
Okay, so I figured it's going to be a waste of time to solve it. But again, feel free. Make sure you tell Megan to do 33. Yeah, I made the key.
Oh.
Of course. All right. A mixture of 1 gram of hydrogen gas and 1 gram of helium is placed in a 1 liter container at 27 degrees Celsius. Calculate the partial pressure of each gas and then calculate the total pressure. So I'm gonna let y'all work on this for about 2 minutes. Try it. And I'm gonna go through a method that I kind of mentioned on Wednesday that could be a shortcut for these types of problems. Are you late?
You can't argue that one, can you?
For 13 minutes? Let me guess, number 2.
Oh, of course.
Okay, that's okay.
Antinyman is respite.
Yeah. To work on number 34, you have exactly 1 minute to solve it.
As of right now, or?
As of right now.
Okay.
All right, 20 seconds. And seconds. And time. All right, let's go over this. So someone in this middle section, tell me the steps, the first thing that you, maybe tell me the equation you wanted to use or that you did use. Hey. Come on. Stay with your chest. I know it's on your paper. You? Anyone in this middle area? nRT divided by volume. Yeah, so that'll get you pressure. Yeah. So you're using the ideal gas law, right? EV equals nRT. EV equals nRT, and then solve for P by isolating it. So you get P equals nRT over V. But now we need to find what? We need to find, yeah, so we need to find moles first, right? So because they gave you mass in this case, we were here on Wednesday, I alluded to using a different equation, which may sound interesting at first because you're like, well, they didn't give us this, or they're not asking for this. But it's using the equation for density of a gas, right? So which is density, again, we don't care about the density, we just look using the equation, which is M over V equals pressure times molar mass over RT. So now, if we see this, we have our mass, which they gave us mass, so we can plug mass directly into the problem. We know the molar mass of each gas, and we're isolating for pressure. So what we can do is just utilize this, solve for pressure, so we get pressure equals mass times RT over molar mass volume. The same thing here. Same thing as up here, right? It's just you're able to plug in all the values that you have. So in this case, for hydrogen, it would be the pressure of hydrogen equal to the mass of hydrogen, which was 1 gram. 0.0821 is our ideal gas constant, right? And this is in liters times atmospheres divided by moles times Kelvin. And then times the temperature, which is always in what? Kelvin, right? So the absolute temperature. So 27 plus 273 is going to give us 300 Kelvin. Divide this all by molar mass of hydrogen gas is what? 2? Yeah.
Approximately 2.
Yeah, approximately 2. We're going to go with 2. So remember, it's H2, so it's not just 1, it's 2 hydrogens, so it'd be 2. And then that's always nice when there's a volume of 1 liter. Pressure of H2 is, in this case, what? What is the pressure? What did y'all get as the partial pressure of H2? Anyone?
12.315.
12.315. This is obviously going to be in atmospheres because once you cancel all your units, you're left with atmospheres as your units. All right. So now you would just do the same exact process, but for helium gas. So how would that, or what does that come out to when you do it? 6.16 atmospheres. Again, so we're just using the same equation. We're just plugging all the information in for helium gas, which is 1 gram of helium gas and then the molar mass of helium. Okay. So now for the total pressure, we just take, this is just Dalton's law of partial pressures, which says the total pressure is equal to the pressure of each individual gas. So you just sum these up and you should get, let's see, 18.475 atmospheres, which equals our E total. So, as we see, not too bad, right? Not too bad. So, Are there any questions on this problem?
It's Rich today.
Rich is actually taking some time off right now. Not feeling well. Yeah. Anyways,
One.
no, thank you. Anyways, how do y'all feel about that problem? Easy peasy lemon squeezy? Yeah, all right, yeah, I think that one's pretty easy peasy lemon squeezy. So let's go ahead and go to, let me find one that might be more interesting. Or did y'all want to stick with gas or go to chapter 6? The thermochemistry. All right, let's see. Consider, how about I go through the problems, I'll scroll, and y'all have to come to a consensus on which problem you want me to go through, okay? So look at problem 35. Let's see.
Water vapor always gets me.
Yeah, this one, what law would you use for 25?
35.
Or what equation?
Volume equals nRT over P.
What do y'all think? Yeah, I think that's probably the better law to use. Again, you can use ideal gas law pretty much for all of these, but then there's more steps. Because again, you like Rich mentioned one time, you can derive all the equations from the ideal gas law. And if you're given enough information, you can use the ideal gas law for each problem, but then it just means there's a lot more steps. So using the other laws might be beneficial. So how do y'all feel about something like 36, where they throw the collected over water?
I need help on those.
All right, let's take a look at this one. So I'll give you 2 minutes, just write down what you, maybe an equation, if you don't know how to solve it all the way, write down at least maybe an equation you think you have to use. And if that's the right equation, good. If not, you make a note to yourself.
Helium at 100 pressure or is the water at 100 pressure?
1 atmosphere. So helium is collected over water at this total pressure. So total pressure is everything, including the water and the helium.
Oh.
All right.
I saw you scavenging on the
Yeah.
You didn't miss too much, and it's being recorded, so you can always, or your wonderful friend kid over there can catch you up.
after YouTube channel.
Oh yeah, make sure you do that too.
Name again?
You know this by now. All right, about 30 more seconds. Again, this is a short amount of time to really finish this problem. If you can, great. If you can't, don't worry. Just worry on Friday, October 20th. That's when you should be worrying. You don't know how to do these problems. But don't worry, everyone here is gonna know how to do it. Is that right? Yeah. Expecting all y'all to get the highest scores. Average. Oh my. Passing grade. They definitely made this easier because it used to be chapters 4, 5, and 6 on exam 2. Yeah, so it was like solubility rules, ionic equations, plus gases, plus thermochemistry. That was actually just up until the summer. This guy. Write that in your top scholar personal statement. All right. Let's go ahead and cover or go over this problem. So let's walk through. Let's do this together. Helium is collected over water at 25 degrees Celsius and a total pressure of 1 atmosphere. So let's break down this problem. Total pressure is talking about what combination of pressures?
Oh, the helium and water.
Yeah, so the pressure of helium plus H2. So when you see a problem like this and you see certain pieces of information, you got to start breaking it down into what it's telling you. So it's saying helium is collected over water at 25 degrees C and 1 atmosphere total pressure. So we know that's incorporating Dalton's law, which tells us the total pressure is equal to the sum of each of those pressures, right? And the question now says, what total volume of gas must be collected to obtain 0.586 grams of helium? And then they tell us that at 25 degrees Celsius, the vapor pressure of water or the partial pressure of water is 23.8 torr. So they gave us enough information to solve this problem, as they should, right? Now the question is, how do we go about doing that?
Find the pressure of water and subtract it from the total pressure, find pressure.
Okay, so what he's suggesting is they give us the total pressure of water, right? 23.8 torr, but we're given the total pressure in atmospheres. So what do we have to do? Yeah, so which one should we convert it to?
Atmosphere.
I agree. I think I would convert it to atmospheres, even though it might be easier to just say 1 atmosphere is 764. That might be easier to say, but going down the line, we're eventually going to have to use atmospheres when we use another equation, like the equation we'll have to use for this. Are we on the same page so far? Cool. So let's convert 23.8 to atmospheres. So someone in the middle section, tell me the conversion factor here. Yeah, I kind of already told y'all, right? It's up there. 1 atmosphere equals 760 torr. So that's the conversion factor, 760. So if we put this into our wonderful calculator, what should we get?
0.0313.
All right. 0.0313 atmosphere. Are you sure? No, that makes sense. You're right. Sorry, I was making you feel like you did something wrong, but you did it right. Sorry. So next,
We lost it.
all right. So this is the partial pressure of water, right? That's what we just calculated. So this is for H2O. And according to Dalton's law, the total pressure, which was 1 atmosphere, is equal to the partial pressure of helium plus the partial pressure of water, which we just found in atmospheres. So we can find this, right? We can find partial pressure of helium because we have these two variables. So let's do that. That's what we're going to do next. And the reason we're going to do that next is because we don't care about how much water we have. We don't care about the combination of the gases. We care about, it's asking us how much helium or what total volume of helium should be collected. All right. So that's why we are doing that. All right. So let's go. Do a different color. Let's do red. So the pressure of helium, the partial pressure of helium is equal to 1 atmosphere, which is our total pressure minus the partial pressure of water. So this should get us
0.9687.
7308. I'm sorry, what did you say? 0.9687. Yeah. 0.9687 atmosphere. All right. So what do we have here? What did we just figure out here? And what are we going to do next? Middle section.
I'll be quiet for a bit.
You're doing good. So we got that. So now what's our next step? All right, we have 6 different equations. What are you going to use? E equals nRT over P. Okay. Again, you were given the grams of helium. So is that the quickest way? Yeah, so you're totally right that we could use the ideal gas, or I almost said ideal gas. It's ideal gas equation, PV equals nRT. You're totally right, we could use this equation. However, the equation that would allow us to go directly to the answer without having to take grams of helium and convert to moles of helium and then plug into this equation is using the derived density equation, right? That we derived to calculate density of the gas, which is M over V equals pressure times the molar mass over RT. And solving for volume, you get mass times RT over pressure and molar mass equals volume. Agree or disagree? All right. Sounds good. So now we just plug in all the stuff that we have here. So the volume equal to the mass, which is 0.586 grams. And the ideal gas constant 0.0821. And then I'm not going to write the units out this time. 25 degrees Celsius in Kelvin is 298 Kelvin. And we just add 273 to that number. And then pressure was, well, what pressure are we using? Yeah, so the partial pressure of the dried helium, because we took the water out, right? It's just a fancier way of saying just the partial pressure of helium. So this was what we got in red, which is 0.9687 atmospheres. And then lastly, the molar mass of helium, which is 4. Oh, yeah, 4, yeah. 4 grams per mole. And if you put that into your wonderful calculator, you get about 3.7 liters of gas should be collected. All right. So as you see these problems, when you break it down, really try to work through them and understand what, principles you're using to get to certain areas. It just begins to seem like a puzzle that you're trying to solve, right? So they give us this information and they want us to do something with it to find another piece of info, which is our answer. But in doing so, we had to use a couple equations, a conversion factor, and then another equation over there, which is Dalton's law. So keep practicing, y'all will do fine. Just any questions on this problem? Ask them now, or else you may never have a chance to ask that question again.
Pressure of water always.
It should be, yes, yeah, because the vapor pressure of water or the partial pressure of water, however it's worded on a test, is always going to be different at different temperatures. So you can't memorize every possible, partial pressure of water when water is a liquid from 0 to 100 degrees Celsius. You're gonna have to memorize 100 different values if that was the case. So no, you're not gonna have to.
Assuming the higher the temperature, the more pressure it is.
Yeah. The higher the temperature, the more vapor pressure. Oh, the higher the vapor pressure of water. Yeah.
Always do pour into the ATM and you solve with the formula.
Yeah, so the reason I did that was because I knew I was gonna have to utilize this equation. Maybe you didn't realize you were gonna have to do that and you would have just used torr. But if I realized I had to use this eventually, I would know that I would have to get my total pressure in atmospheres eventually, because our ideal gas constant is in units of liters atmospheres, not liters torr or liters millimeters of mercury. So again, I converted to atmospheres because I knew I was gonna have to do that. If you had done this in torr and your partial pressure of helium was in torr, that's fine. But if you want to use this equation, you have to end up converting that number, which was in torr, to atmospheres.
You still have to.
Yeah, so that's a good question. So I knew I had to use this equation because one, it's not a before and after scenario, right? It's not giving us let's find some of those problems that we did previously. So number 20, a sample of this gas occupies this volume, temperature, and pressure in this one state, and it's saying find its volume in a different state. That's before, after. So that's how I know that I'm not using any of those equations that are M1V or not M1V1. P1V1 equals P2V2, because those are all before, after scenarios, or Charles's law, any of those. So that really narrows down your equations to either Graham's law, which we did on Wednesday, or ideal gas equation, and Dalton's law or something. So that's how I was able to limit it or narrow down which equation I have to use. And because I eventually know I have to get Graham, or not Graham's volume, and we're given mass, then we can utilize this equation to find our V, right? So just keep working, do these problems, definitely, if you can, find time, do these problems. They're very helpful because they help you. I feel like the biggest challenge is knowing what equation to use for which problem, right? Because you are given so many equations. So doing more problems will help you be able to identify that, because you're like, hey, I've done a problem like this and I used an equation like this because this was the scenario, But definitely do that. So 37 is similar to 36. I don't want to do all of these. I want to give y'all some of these types of questions to do on your own time, because these are the questions that I feel like students have the most difficult time with. Let's do 39. It's a little bit of a throw it back, and then 40 is also a good one. Ooh, 40 is where we start getting into chapter 6. We'll do those. Are there any trigger words for y'all? STP, yeah, that's one. Is there another one that indicates an equation that you should use? Density is another one, right? Because what's the equation for density of a gas?
Pressure times molar mass or constant rate times temperature.
RT. Yeah, so those are some trigger words. STP is one of them. I told y'all, make that a word that as soon as you see it, you think of two conditions. And then the other one is density. That one is going to tell you which equation you want to use. So there you go.
Density is
What do you mean?
like it's giving you density of mass over volume. Like we don't have the molar mass of it.
You're exactly, we don't have a molar mass. And they're asking us to identify the gas. So what is something you're going to have to solve for? There you go. So we don't need molar mass because we're solving for molar mass. And then pressure is given because our trigger word told us pressure. Temperature T is also given again because STP. And then R is just a constant. Tattoo that one on you. You're going to need it.
But wouldn't it be pressure times density for constant rate?
I do not believe so. Pressure times density. I don't think that could happen if you manipulate this equation. What are we solving for? So isolate molar mass. All right, about 20 seconds. Need a fresh cut recently? Did Riza? Yeah. Does he tell y'all to call him Riza?
I just know about Rishon.
What he said though, that's why I like Riggs. He's like, let's have a heart to heart, and he always says that. I love my student,
Oh,
and then everyone was like,
dude, he's like the most amazing professor I've ever had. He's like, yes, agree, yes. When you do this, this is what? Agree? Yes. And he wants everyone to say yes. All right, anyways. Sorry, got a little off topic there. We're just talking about our calculus. My old calculus, his current calculus professor. Great guy. All right. So we are asked, what is the identity of the gas? And someone in the middle row or section again, help me out here. Equation, or never mind, I already told you that. So what do we do next? Plug in, right? So let's go ahead and solve for molar mass, right? Because that's going to tell us the identity of the gas. So this is equal to density times R times T over pressure, right? So now just plug in. Because I multiplied both sides by R and T, right? So multiply both sides by RT to get DRT on top, and then divide by pressure on both sides.
oh,
Yeah. So plugging in info, 3.164 grams 0.0821. And then temperature was 273 Kelvin. Remember, it's always in Kelvin. Pressure was 1 atmosphere. And what did y'all get for your molar mass? 70.95 grams. Everyone else confirm or not confirm? The opposite of confirming. Declining, denying. That's fine. Yeah, there's probably some rounding error or something. So as long as you didn't get like 80.95, you're fine. So what is the identity of the gas? Chlorine? Yeah, right. So you might look at your noble. Oh wait, sorry, it's unknown diatomic gas. So you might be looking at all those things on the periodic table and saying, hey, none of these have a molar mass. These are diatomic elements, right? So their molar mass is twice of that of the atom they came from, right? So this would be chlorine because chlorine is about 35.45, which equates pretty close to 70.95. Yeah, so the molar mass of this compound, or no, not compound, because it's not a compound because it's a diatomic gas, right?
Here's some information.
It's a so diatomic, right? So we know
So you divide it by 2.
you can divide it by 2 to find the individual weight of just the atom. That'll lead you directly to what it is, as long as you just recall that it's a diatomic gas. So it has to be either chlorine, oxygen, nitrogen, chlorine, bromine, or iodine. But to be honest, bromine and iodine are both not gases at this current temperature. So I mean, it wouldn't make sense for them to be in this problem. All right. So this is where the exciting stuff, what I've been waiting for 7 weeks. Got so tired. I love my students, but I started hating the basic stuff that we kept doing for 5, 6 weeks straight. All right. Anyways, now we go into more interesting stuff. So question 40 is saying it's not a question because I had just implemented this like the day before an exam at one point. But it's just, you need to be able to describe what is going on in each scenario in terms of work. Now, what is work? Yeah, so work is a unit of energy. So when we are talking about gases specifically, and we're talking about work can either be done on a gas or it can be done by a gas. So if you take a deflated balloon, right, and you blow it up, you're expanding the size of the balloon, right? So that balloon is actually, or the gas in the balloon is pushing on the balloon to expand it, right? So that gas is doing work on the surroundings, all right? So in that case, if we're doing work on the surroundings, we're losing energy, right? Like think about it if you're gonna go for a walk. If you're gonna go for a walk, you're expending energy. Therefore, you're doing work, whether it's pushing on the ground, whether you think about that or not when you're going for a walk. So when you inflate that balloon, the gas inside the balloon is doing work on the balloon, which is doing work on the surroundings. So that gas is going to have a negative value of work associated with it. Again, work is just you can just think of it as energy being done by something or being done on something. Whereas if I took that balloon and it was closed and I squeezed that balloon, I'm an external force doing work on the balloon. So the volume of the balloon is going to decrease, but it's not because the gas is doing work. It's because I'm doing work on the gas. In order to get it to that state, I have to do work on the system. So if you haven't watched any of the videos, this might be all very new stuff, so it might not resonate and, sit right with you at first. So I encourage you after this, if you have time this weekend, watch some of the videos. If you're in our moms class, watch the videos that you're gonna go over on, or that's due on Tuesday. And yeah. So if we look at these two things here. The top one is talking about our initial state, as denoted by the V initial, talking about the initial volume, all right? Whereas the bottom two are two separate states. So again, they're not supposed to be happening at the same time. It's just saying if this happened, what is happening in terms of work? Or if this happened, what is happening in terms of work? Okay, that's how you're gonna see it on the exam. So on an exam, you're either gonna be given these two or these two. You're not gonna be given both of those, all right? So if we start at the top and go to the one on the left, what could we say about the gas and in terms of work? Or let's think even more simpler. Is the volume getting smaller or is it getting larger? Y'all agree or disagree? Y'all agree or disagree in the middle? Yes,
Well, on
Go-
A, the volume's getting.
you're talking about, yeah. Yeah, so volume's getting larger, right? So going back to our balloon analogy, when the balloon's getting larger, the gas is doing positive or negative work.
Larger it's doing.
Yeah, so the gas is doing work on the surroundings, right? Therefore, the gas is losing energy, therefore negative
Okay, it's
work.
not bouncing around as much.
I mean,
I guess the particles aren't bouncing as much.
so the particles are pushing on the system to expand the volume. Therefore, the gas is doing work to make the volume expand. Therefore, if the gas is doing the work, the gas is gonna have negative amount of work associated with it.
You said the gas doesn't work. Which is it against it? How come it doesn't do more work?
What?
Why is it negative work?
It's negative work because the gas is the one utilizing its energy to make the volume bigger.
It's not itself doing.
Yeah, so it's losing energy. Remember, work is just energy,
Okay.
right? So by negative work, we mean that the gas is losing energy, right? Now you can never have negative energy. The work is associated with a change in energy, all right?
So it's expending more
Hold on.
energy to push up.
Hold on. I'll get to you in a second. What's up?
Less.
So the more volume, as in you're saying, going from here to here. So it's increasing in volume. The gas is losing energy, right? Because that's as denoted by negative work. So yeah, technically, they would have less energy associated with those gas molecules when you go from there to here. Yeah, because remember, energy is being conserved, right? So if I'm pushing on that piston or whatever this cylinder thing is, I'm pushing on it, I'm transferring energy from me into that system, which means that energy has to be conserved. So if I'm losing it, that means the gas has to be gaining it, right? So in this case, some external force is pushing down on this little cylinder right here. Because it's pushing down on it, would you say the gas is doing work or the gas is getting work done onto it?
It's being worked on it.
Right? So therefore it's gonna have a positive work value because it's gonna be increasing its energy, right? Because something's having to put energy into this system in order to make this go down. So this one would have a positive work. So this is back to gas laws. I don't want to do gas laws. We'll do gas laws if y'all want to do gas laws, but. Another one, out of curiosity, what do y'all think the equation might be for these problems 41 and 42? 41 and 42.
Gotta get the,
So, well, I'm not asking for the process, what equation?
multiple steps.
Like the main equation you're going to use to solve this, which is Graham's law, right? Has more mass in it, but the name of the law is called Graham's law. So that's what I was just looking for. And it's, are there any words on there that make you think of that? Effuses, right? And they also give you time. So these two words, effuses or diffuses, should begin the process of recalling Graham's law, right? Oh gosh. And so 43 kind of is just going back to what David was talking about at the very beginning of class. Or not class, this thing we have, this little session. All right. So gases do not behave ideally, but under what conditions does a real gas behave most ideally in terms of pressure and temperature?
Low temperature, sorry, high temperature, low.
Yeah. So those are the two things we're gonna have to remember. I have seen a lot of questions that ask you that basically the answer choice is increased or high temperature, low pressure. Because it's asking you basically the same thing, but in a multiple choice style question. All right. It's because the interactions between the, yeah, because the postulates that you make, they're just assumptions in order to create these equations. You didn't make those assumptions, then these equations would not work. In fact, because we're only using algebra, they honestly don't work. But it doesn't work because in real life, they're not point particles. You know, in real life, they interact on each other. And in real life, not all the collisions are completely elastic. You know? So that's exactly why real gases do not behave like an ideal gas that we discuss in class. Let's move to 44. And this is going to be talking about internal energy. So internal energy is basically just all the energy in a system summed up. Okay? So that's always denoted by delta E. And this is always going to be equal to the heat in the system or heat released by the system. Or it's really a sum of everything. But when we put that delta E in there, we're talking about the change in internal energy. So the change in internal energy is equal to the heat gained or lost and the work done on the system or by the system. Okay. So heat is going to be denoted as Q, work, luckily that one's a W. Okay. So internal energy is just all the energies summed up in a system, which would be denoted as E. But because we're talking about delta or the triangle delta E, change in internal energy, we're going to be utilizing this equation to calculate the change in internal energy, which is equal to the heat Q lost or gained by the system. So you can kind of think of that if you have, let's just say you take a bowl of boiling water and you dip it or you put it in a bucket of ice. That's obviously going to take heat away from the boiling water, right? If you put it into a bucket of ice. Therefore, the Q associated with that transformation would be, what do y'all think, positive or negative? If we're losing heat. Because remember, we're the water. We're boiling and we're being put into a cold environment. Are we going to gain heat or lose heat? Lose, right? So we denote losing things, whether it's losing energy, work, or losing heat, Q, with a negative sign, all right?
The delta E is change in energy or?
Change in internal energy, yeah. So 44 says a system receives, so that means the system is gaining, right? Gaining 425 joules of heat. So when we think of that, we should be thinking of, we should already be associating a positive or a negative sign with that statement and for the variable that it tells us. So a system receives 425 joules of heat from its surroundings. Is that going to be positive or negative? Positive, right? The system's receiving, so that means the system's increasing its energy because it's taking in by that source. So that's going to be plus Q, or plus 425, right? Because the Q is 425 and the receives tells us that it's positive. Right? And it delivers, the system delivers 425 joules of work to its surroundings. So the system delivers 425 joules of work to its surroundings. So if I'm the system and I'm delivering joules to the surroundings, am I losing or gaining that energy? Losing, right? Because I'm giving that 425 to the surroundings. So that's going to be associated with a negative or positive value. Negative, right? Does everyone agree?
What's losing it means
Yeah, negative work. That means that the system's doing work on the surroundings. So because it delivers 425 joules of work to its surroundings, that means energy, the 425 joules is going from the system to the surroundings, and we associate that with it's losing the energy, therefore it's negative energy. So this is negative 425. So when we put that into our delta E equation, which is change in internal energy, there's plus 425 kilojoules and minus 425, not kilojoules, I'm sorry, it's joules. Minus 425 joules, which equals, there's not a net change in internal energy. The change in internal energy is 0, right? So again, could have gotten a couple answers. You could have either gotten negative or 850 or positive 850 if you assign the values wrong, or 0 if you assign them right. So that's how we would do that problem. Okay, let's do a different one, number 45. What is the change in internal energy in joules of a system that releases 675 joules of thermal energy? Thermal, is that going to be heat or work? Yeah, heat. So 675 joules of thermal energy to its surroundings that's what's being released, and 530 calories of work is being done onto the system. So let's associate these with signs, plus or minus. Yeah. Yeah, the answer is 0. So it should be 0 joules, I guess. Delta, the change in internal energy is 0 joules. There's net movement of 0 going in and out. All right. So a system releases 675 joules of thermal energy to its surroundings. Is that positive or negative? Are you sure? Okay, yeah, that's right. So 675 joules of thermal energy is released, so it's going to be negative 675 joules. And then 530 calories of work is done on it. Negative or positive? Positive, right? Because work's being done on the system, that means something is putting energy into the system in the form of work. If something's putting energy into the system, that means the system's gaining that energy. So it's gonna be positive, so negative 530 joules. Our delta E is equal to Q plus W. But we gotta be careful about the units that we have here.
Wait, didn't you say it's gaining work?
Surroundings.
Work's being done on it.
Oh, yeah, you're right. I'm sorry.
It should be positive 500.
Yeah, you're right. So the releases, yes, and then done on it. I was just testing you, man. And you passed the test. Good job. All right, anyways. Has anyone read ahead? Who's gonna make me a happy camper? This guy is cheating, man. You're cheating.
How much cheating?
Using your resources. No, I'm just kidding. Only on test day. All right. What is the conversion from calories to joules?
Calorie equals.
Which one is it? I'm hearing two different things from you. Yeah, so 1 calorie is equal to 4.184 joules. That is an important conversion that you have to 4.184. Yeah, that is an important equation that you're gonna have to know. And this is good for people in our Mons class. You're gonna have iClicker questions like this on Tuesday, so I mean, good job. You'll hopefully do better than everyone else. All right. So what is the change in internal energy? Blah, 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 blah. So the definition of a calorie is the amount of energy required to heat up 1 gram of water by 1 degree Celsius. So that's why it takes 4.184 joules of energy to heat up 1 gram of water by 1 degree Celsius. Although this number will also be important later on, 4.184. So now we just use our conversion factor. So 1 cal equals 4.184 joules. What does that give me?
We get 2,217.52.
17.52 joules. So that's a positive number, right? Because it's being done on the system, the work. So now we just add these up. So we have delta E was negative 75 for Q, right? So negative 675 joules plus the positive amount of work, which was 2217.52 joules. And this gives me what? That's my answer.
1,540.
Well, yeah, because we had joules and we added joules to that, so our final unit will be joules. That's what the problem is asking for. Oh, interest. 46 is gonna be different kind of equation. All right, how many of y'all want to do one more problem that will introduce a new equation that you'll probably be like, all right, what the hell did we just do? Yeah? How many of y'all just want to go home? This guy. Oh, you raise your hand. Yeah, what? After, okay, there we go. All right. So find Q when 22 grams of water is heated from 25 to 100 degrees Celsius. All right. Are we using internal energy anymore? Right? They didn't give us any information about work. They just told us to find Q. They didn't even give us information about internal energy. So we are out of luck in terms of using our simple equation, which was just basic addition, Q plus W. Has anyone learned the other equation that we're going to be using? It is Q equals MCAT. And if you don't know it, that's okay. Colin should know it, right? took this in high school. Or this was the chapter you blanked out, right? At least you remember the MCAT equation. All right, so Q, what's Q again? What? It's heat, right? Not internal energy. That's delta E, or that's E. Q is equal to the mass of some substance times C, which is known as our specific heat, and times the change delta in temperature of the system. So Q equals MC delta T. A quick way to remember it is just by saying Q equals MCAT for all you pre-meds out there.
E is constant.
T is the specific heat, and it's specific to every substance. The one that you're gonna have to know is the specific heat of water,
E is change.
temperature. All right, so the specific heat of water is 4.184 joules per gram. So joules divided by grams degrees Celsius. Just like that. So that is the specific heat for water. This is something you're gonna have to bring to the test with you. You're not gonna be given the specific heat of water. It's gonna be expected that you know that for whatever reason, okay? It's just another value, but luckily it's the same value as the conversion up there, which is 1 cal equals 4.184 joules. This is just 4.184 joules. Because remember, the definition of a calorie was the amount of energy in joules to heat up 1 gram of water at 1 degree Celsius, which this literally tells you the energy per gram degree Celsius. So that's where we get that number from. So because we're talking about a change in temperature, it doesn't matter, because now if you're going from Fahrenheit to Celsius, that's different because there's multiplication and division associated with that, but because Kelvin and Celsius are related to each other just by adding or subtracting a number, it doesn't matter in terms of the change. All right. Yeah, so C is the specific heat, and it's the specific heat of a substance. So the specific heat of a substance is the amount of energy, which is, it's always going to be in units of joules per, or energy per mass, or per weight and temperature, because the definition of specific heat is the amount of energy to raise 1 gram of substance by 1 degree Celsius. Okay, so that's what C is.
Should we change the Kelvin or keep it at?
So it doesn't matter, because what we're dealing with is the change in temperature. So whether you did, I'll show you right here. So 20, if we change the initial temperature 25 to Kelvin, it would be 298 Kelvin. And then if you changed 100 degrees Celsius to Kelvin, it would be 373 degrees Kelvin. Or 373 Kelvin, right? So whether you, and the delta just means the change in, so you do final minus initial. So the final minus initial would be 373 minus 298 equals 75 Kelvin. And if you just did that with these two, you would get a change of temperature of 75 degrees Celsius. See that? So that's why it doesn't matter whether it's in Kelvin or Celsius, but that's only for these problems. Okay? You see a gas in a problem and it's asking you, you have to use gas laws, Kelvin, all right? But if it's something like thermochemistry, chapter 6 topics, it doesn't matter, Kelvin, it doesn't have to be your unit of temperature. Got it? Everyone understand? Everyone? Yes? Good? All right. So the way we use this equation is going to, if we're finding Q, then we just plug in all the other numbers that were given. So Q equals 22 grams of water times the specific heat of water. So again, this is something that you're going to have to bring to the table. We're not going to give you that. Something you have to bring. the change in temperature. So again, the change in temperature is on the final temperature minus the initial temperature. The final temperature was 100 degrees Celsius minus the initial temperature of 25 degrees Celsius. So delta T equals 75 degrees Celsius. 75. Plug this into our calculator. Q will give us that'll give us a number for of what? 6,903.6 in units of what?
Joules.
Joules, right? Because look, everything cancels out except for joules. Grams cancels, degrees Celsius cancels. We're left with joules. So joules. So that's the most, and I purposely made this the easiest calorimetry problem to give y'all at the beginning, because I wouldn't want to give you something. Here, I'll show you the more difficult ones.
Don't scare us off. Scare us off, please.
You're gonna have to see this eventually, so you might as well face your enemy now. All right, this is not even bad. So something like 65 is where probably the hardest one you're gonna have to be able to solve. You don't have to drink coffee.
That scares me, bro.
The enthalpy change is like the heat associated with the chemical reaction. So it's can be positive or negative, and that's going to determine whether the reaction is endothermic or exothermic. We'll get to that stuff, those terms later. Don't worry about that now. Just go into the weekend knowing that on Monday we're going to go over more of these problems. All right. So again, I wouldn't want to throw you into the water. I put you in the shallow end over here when it came to these coffee cup problems. I wouldn't want to scare you off today. Thank you for coming. And I know Mr. Yellow Shirt over here wants to get home so bad that you can do that now. I'll stick around for a second if you have a question or two. Feel free to ask.